afternoon. Welcome everyone. It's a pleasure for me to introduce you Eng.º. He's a good friend of mine, and he's a consulting engineer in the field of energy efficiency, mainly in the areas of heating, ventilation, and air conditioning. Carlos is, he looks very young, but he has been working almost 30 years in this field. So we started with, after graduating in mechanical engineering at the IST in Lisboa, he has done a graduation course related with energy audit and management, and worked as an independent professional in this area 2 years. And after he joined an HVAC company, and in 1995 he started his own company. And is known as one of the best designers in this area in Europe. I can assure you, because I have some information about this field. And he was the president of the direction board of the Eng.º, which is the Portuguese Association of Engineers in the heating, ventilation, and air conditioning. And recently he was involved in a transcontinental project. It was a guy who has been the first guy who published in association by Eng.º, the American Society for Heating, Ventilation, and Air Conditioning, and RIVA. RIVA is the Federation of the European Association. So there was a first experience of publishing a common guidebook, and Thomas was one of the co-authors of this guidebook about active and passive heat application. So this is a design guide. He has been also teaching in a postgraduate course about sustainable construction in the new University of Lisbon. Okay, so you came here to listen, not to listen. So thank you very much.
Thank you very much for the kind words. Actually, I've been practicing in HVAC for 28 years now, and I hope I can bring to you some of my experience in how I look at how can we do zero energy buildings. It's a pleasure to be here in Eng.º and in this historical university, and it's also an honor. And I hope I will do my best to deserve it. So, I think zero energy buildings are a paradigm shift. And I will quote Thomas Kahn literally. He said that the successive transition from one paradigm to another, the revolution, and I stress revolution, is the usual development pattern of mature science. And actually, zero energy buildings is a revolution in the building industry. We with this big change, we will have to ask new questions, change the rules of the business, direct new research, and we have to work in a different way to achieve this very challenging goal. And what brings this big change actually as a mandatory change? In Europe, we have the EPBD directive. I think you all know this directive. This Energy Performance of Buildings directive was published in 2010. And in the United States, we have this document that was published 19th of March 2015 this year, planning for federal sustainability in the next decade. So, both in the United States and in Europe, we have to do zero energy buildings. It's not an option. We have to. And I will just go in certain aspects of both documents so that you can see what the Americans have to do and what we in Europe have to do. First, I show this definition of net zero energy building in the United States law. First, this executive order from President Barack Obama applies to all federal buildings. It does not apply to privately owned buildings like in Europe. Okay? So they have the definition of net zero energy building, which is this one. It means a building that is designed, constructed, or renovated and operated in such a way that the actual annual source energy consumption is balanced by on-site renewable energy. It's a very simple concept. What you use in energy, you have to supply with renewables. And you have this balance, and it has to be zero. It's a very simple definition. Also, this other point of the document states that beginning in 2020, 5 years from now, every new building, new governmental building in the United States has mandatory, has to be designed to be zero energy. Okay? From beginning in 2020. All buildings that have more than 500 square meters of gross area have to be zero energy. Also, there is something stated about existing buildings. Not all existing buildings have to be zero energy, but a percentage of them should be zero energy. They do not specify what is the percentage, but also these buildings, only those that are above 500 square meters gross area. And also they have the goal to reduce the global energy consumption of all federal buildings by 2.5% each year. So, this is the United States that published this executive order in March, and then in September, the Department of Energy clarified some things that are important. For instance, the definition of zero energy building is now an energy efficient building where, on a source energy basis, the actual annual delivered energy is less than or equal to the on-site renewable exported energy. There is a small difference, because with this first definition, it was not stated that the building had to be energy efficient. So we could have a traditional building intensively consuming energy, as long as we had a mega renewable energy production, we would be net zero, okay? Not anymore from September. It has to be energy efficient. And also a definition of what is on-site renewable energy. What is on-site? And the Americans define it as the energy that is produced inside the building boundary. Okay? That's very limited. I would say, for instance, that biomass, wood pellets, for instance, would never be produced inside the building boundary. So, this definition excludes the use of biomass from renewable energy, not renewable. You will see that the definition is slightly different. Also, other important issue is that this process has to be done in primary energy. So, if you have photovoltaics and you are depending on the efficiency of the production and distribution of electricity in the country, in Europe, by law, we have to consider an efficiency of 40%. You cannot balance use the electricity at the building with the electricity produced by photovoltaics. You have to divide it by the efficiency of the electrical distribution network. Okay? So it's much more demanding to work on source energy than in final energy. In Europe, we have the EPBD, and we have a very subjective definition of zero energy buildings. We have nearly zero energy buildings, not net. It's a big difference. It's not net and net zero, it's nearly zero. And it means it's a building that has a very high energy performance. And the nearly zero or very low amount of energy required should be covered to a very significant extent, and that is subjectivity, by energy from renewable sources, including energy from renewable sources produced on-site or nearby, another subjective, nearby. So we have three not very well defined things here. Nearly, very low amount of energy, nearby, well, each country will define this parameter. Then we have the goals in terms of dates. When should we comply with this obligation? By 31 December 2020, all new buildings, public or private, must be zero energy, nearly zero energy buildings. So, we are 5 years from that date, so buildings that are being started next year will have to be designed and conceived to be zero energy. I don't think anyone is doing it, or a very small percentage of people is doing it. But for public buildings, it's 2 years earlier, so it's 2018. It's more. And this subjectivity of the definition can be defined by each European country freely. So each country will define what is nearly zero, will define what is a significant extent, what the percentage of energy should be balanced by renewables, will define on-site and nearby. So, and already there are a few countries that have already done This, and the definitions are very different from country to country. In Portugal, we still don't have this job done. We are late. We are late. We should have already done this. So, this is what drives the industry, the building industry for New Zealand. We will have to do it. I think people in the area haven't really quite realized this. Because in Europe, this is now. This is now. We have to do it now. It's different. But how can we get it? And now I will show you a very simple example in order to make it easy to tell you the way to get to zero energy. So I will have a very simple example of a system, an energy consumption system in buildings that exist in buildings, and this concept could be applied to all the buildings. This is a very simple system to produce hot water for showers in a gymnasium. Domestic hot water. We have a boiler, and this boiler produces hot water exclusively for showers in the gymnasium. Just to make it simple so that I can explain it better. This chart is a sampling chart, and the width of the arrows is proportional to the amount of energy. Okay? And so this chart shows how energy is used in this system that produces domestic hot water. Primary energy enters in the system, and we have 140 units, doesn't matter what units they are. 140. We have the boiler losses, and this is about 11% efficiency. 11% losses, not 89% efficient boiler on average yearly, which is a very good efficiency. It's not a nominal efficiency, it's a yearly efficiency, because there are periods when the boiler comes on and turns off. And when we have an average yearly efficiency, we have always a much lower efficiency than the nominal efficiency of the water. Okay? So to have 89% efficiency is good, actually, in practice. And then we have system losses, and I will explain you what these system losses are. In hot water systems, in buildings, system losses are huge. Most of existing buildings have hot water systems that are dramatically inefficient. And I will say why. Again, we have the boiler losses, the system losses, and then we have the final useful energy for the showers. Okay? And so this equation shows that primary energy is 1.4 of the final useful energy, okay, in this system. And how can we get from here to zeros? First, we take care of the system losses. It makes no sense, of course, we could start here and install a mega solar thermal system that would cost billions and just take care of this 140. It's not the right way. First, we should reduce waste and have an efficient system. The first thing is to reduce system losses. And we can reduce system losses in a domestic hot water system by benefiting the insulation, because many systems, most of the existing systems, have huge amounts of piping that is not insulated. We can balance and minimize return water flow, because these systems always have water that's stored in big storage tanks, and then there is always a circulation of water 24 hours a day to keep the water in the pipes always at useful temperature, not to make the pipes cool. So there is always a pump running 24 hours a day, 365 days a year. And usually these pumps are over-dimensioned. Water flows excessively, and this is actually we have a huge radiator of energy working 8,760 hours per year, losing energy. So we have to insulate these pipes, we have to reduce the water that always is circulating, and we have to balance the water flows. And finally, we can change the strategy to fight the bacterial legionella. I think most of you know what it is. We have to, the usual strategy to fight legionella is to have the tanks with water at 60 degrees, and from time to time, bring them to 70 degrees to kill the bacteria. And so this is very energy expensive. So we can have a strategy for legionella which is not thermal. We can have a chemical strategy to fight legionella and have the tanks at 50 degrees instead of 60. And that's a huge benefit. And implementing these measures, we can go to a rather acceptable level of losses in the system. Okay? So we have reduced a lot the system losses. Next step, and this is huge, we can change the shower heads. Most shower heads, in Portugal for instance, we have this system, have water flows between 12 and 16 liters per minute. And these are inefficient shower heads, traditional shower heads that you can buy in any plumber in the corner shop. But if you go and find the best, the more efficient shower heads, you can have a good shower head with 6 liters per minute. And I would say that all of us, in the last 10 years, systems like this one that have 6 liters per minute in a shower head. If you go anywhere, you will find it. You will find 12, 16 liters per minute. And you can go down to 6. And if you go down from 12 to 6, you reduce by 2.5 the needs of the final useful energy. Okay? So we have now a very different perspective from the first one. And now is the time to bring renewables. Now we just have, you see, around 60 units of primary energy. Remember that in the first slide we had 140. Right? We have reduced from 140 to 60 with measures that are very low cost. Measures, investment that pays for itself in less than a year. In months. So we should do this first before using the renewable. Now we will use solar thermal, of course. It's the best, most adapted renewable to produce hot water. And if we have a solar thermal system, we can expect on average to have 70% in Lisbon, Portugal, 70% of the needs supplied by the solar thermal system. And then we will only need 30% of the backup energy from the boilers. Okay? And now we are reduced to 23 units of primary energy. Okay? From 140. And this, at this stage, we could already be nearly zero, depending on the definition of the country. What is nearly zero? How near to zero should you be? But you can do less, because we have such a small amount of energy that is required on top of renewables. You can add an heat pump. An heat pump is also renewable energy. Why? Because the heat pump will extract heat from the atmosphere with the use of around 1/3 of this energy to drive the compressor. So the heat pump will extract energy from the atmosphere and deliver this amount of energy that's required. And now, at this point, we are just using 7 units of electricity. And this is very close to the unit zero. Of course, this part of the chart was calculated based on the European directive that states that we should use for this kind of calculations an efficiency of 40% for the production and distribution of electricity. And so, to have these 7 units, we are to use 70.5 units of primary energy. Okay? So we are just changing from 23 to 70.5. Actually, this is what's stated in the directive. But in Portugal, last year in Portugal, 62% of all the electrical energy used was produced by renewables. 62% of all electricity in Portugal last year, in 2014, was produced by renewables. So, if we are just using 7, we are really close to really zero. But we are just 7. If we have a small photovoltaic, we will cover this 7. And then this is zero energy. Okay? Net zero, not new. This is net zero. And this is the first chart that we began with. And we will see the types of measures that we took to achieve to zero energy. First, energy efficiency. We reduced this part. Then, changing requirements. We reduced the requirement of 12 liters per minute per head shower to 6. So we changed the requirement using technology. And finally we used renewables. We used a mix of 3 renewables: solar thermal, heat pump, and solar photovoltaics. And I would say that now we will go to the roadmap. These measures should all be taken, but the order is not any order. They should be taken in a certain order. And the roadmap, I would say that the first kind of measures that should be taken are measures to change or reduce the requirements. The traditional requirements. And this example is good because you say, okay, we change the shower head from 12 to 6, but we will have a bad shower. We don't. In some cases, maybe we will have to go to this point. Because actually, this is a change of paradigm. We have to change everything. The way we thought before now has to be different, which is zero energy. Of course, these shower heads that work with 6 liters per minute were designed and conceived and tested to deliver a good shower. Perhaps it's not exactly the same shower. It's a change in requirements. Then we should stress on energy efficiency. Finally, renewables. Not finally. Because actually, remember, I stressed in the United States definition that it also applies in Europe. We don't want to design zero energy buildings. We want to have zero energy buildings in operation. We have to make sure that these buildings that we design will actually operate with a zero energy balance. So, we have to do energy monitoring. after the building is constructed and operated. So these are the 4 steps we have to take to get to this goal of zero energy. And now we'll go a little bit on each one of them. Now, not just in domestic hot water, but generally in the building. What are the requirements that we should re-evaluate? Thermal comfort, indoor air quality, lighting, office equipment loads, personal computers and all this stuff, energy flexibility, and I will go on each one of them, each one of these now. First, on thermal comfort, I will start to show you this chart that shows in the horizontal axis indoor air temperature and in the vertical axis cooling energy. And this chart was made by me in an actual consultancy for a client, in which I measured actually the energy consumption of the air conditioning system with different indoor air temperatures. It was a very stable solution. Actually, it was a telecommunications room. It was a true telecommunications room in which the internal loads were very constant. It was a very good example to measure this influence of indoor temperature on HVAC efficiency. And what this chart shows is that, on average, each degree Celsius that we increase the indoor air temperature implies a 5% increase in energy consumption on the air conditioning system. This was measured by me, and actually it is in agreement with lots of articles published on this issue. So it's very important to have in the summer the higher temperatures that we can have indoors, and in the winter to have the lowest possible inside the comfort range. Okay? And now I show you this part of a standard, the national standard ISO 7730, which is a standard of thermal comfort. And it defines what is adaptation, because actually people can feel comfortable with different environmental conditions if some conditions are applied. In this standard, they say that extended acceptable environments may be applied for occupant controlled, naturally conditioned spaces in warm climates or during warm periods where thermal conditions of the space are regulated primarily by the occupants through the opening and closing of windows. Field experiments that show that occupants of such buildings could accept higher temperatures than those predicted by PNV. PNV is the way to determine the comfort. So if we apply some rules in the use of the building, we can have higher temperatures. And if we have higher temperatures, we use less energy. For instance, from this standard, we have this chart that shows in the horizontal axis the mean monthly outdoor air temperature, and in the vertical chart, indoor comparative temperature. And this gray area is the area inside which we have over 90% acceptability from the occupants. And this lighter gray is 80%. Okay, let's go to 90. For instance, in Lisbon, maybe we will be the same. We have an average in the summer of 25 degrees Celsius outdoors. at 90%, we could have 28 degrees indoors using adaptive comfort criteria instead of the traditional comfort criteria. Okay? Other issue, this is another example from the standard, and that shows that we can, if we have higher air velocities, everybody knows that. If you are hot, if you install a small fan in the desk, you feel more comfortable. If the air conditioning system delivers a higher velocity, you can have higher temperature. So that's another way to get there. Of course, there are other issues that are not shown, but I would recommend to study this standard 7730. Of course, clothing is another issue. If you are dressed with a tie and a jacket, and you require maybe 23, 24 to be comfortable. But if you are allowed to work without a tie and short sleeves, and even if you can use shorts, maybe you will be comfortable with 28, 29. So we can change and we will change the dress code. For instance, Japan was the first country to do it with movies and hobbies. All the Northern Indians in Japan, maybe around 10 years ago, started to be done in the summer without ties and jackets, to give an example. And in France, also the same thing, and public buildings in France today are mandatorily regulated to 28 degrees Celsius in summer. So, this is examples of how can we, what steps can we do. So, we have adaptive comfort criteria. We can have natural ventilation whenever possible. Of course, if it's -20 and snow, we cannot open the window. But we should use, whenever possible, natural ventilation. Occupant control of the indoor environment. It's known that if the occupants have control of their environment, they will be more satisfied than if they do not have. Of course, in an open-class office building, we cannot have occupant control because we have 100 people, 100 persons in 500 square meters, so we have to control the temperature for everyone. So we will have a percentage of unsatisfied occupants. But if we have the individual cellular office, you should be able to control everything, including opening the window. Of course, with the window switch, if you open the window, automatically the air conditioning is closed. Use of higher velocities in the summer, for instance, in the United States, ASHRAE standard 55 and 1 has a big change in the last version on this issue to use higher velocities to increase indoor air temperature. The flexible dress code that I mentioned, flexible use of indoor space. Of course, if you have to work in this chair, in this table, and if you are not comfortable here because of radiation from the window, hot radiation from the window, or whatever, if you have no choice but being here, you will need a lower indoor air temperature. But if you can move from here to here, maybe you can be comfortable anyway without reducing the indoor air temperature. The flexible use of the space, of indoor space, and also flexible working schedules also. I think this is all new things. We have to bring new ideas to the table to get to zero emission buildings. And they are all kinds of new ideas, different from what we used to do before. Now, on indoor air quality. I will show first this chart from the Department of Energy of the United States. This chart was built based on some thousand buildings. And what does it show? The chart on the left shows the energy consumption, no, not the energy consumption, the power, the electrical power installed in air conditioning systems. Indeed, 3 different types of air conditioning systems. This last one is very used in the United States, almost not used in Europe, only in, for instance, in big malls, in big, like continent or something like that. And this chart on the left shows the power, the installed power. And the part, the white part of this stacked bar is the chiller, the equipment that produces chilled water for the air conditioning. And the green part are fans. And all these other parts are fans and pumps. Okay? And you see that when we look at power, kilowatts, we see that majority of the power is in the chiller, in the compressor. But this chart on the right shows energy, annual energy, not power. And we, if we look on the right, we see that fans and pumps use more energy than the chillers. So we spend huge amounts of energy to circulate air in the building. And most of the times also to circulate water, which is incredible. We should. But actually, I have experienced auditing buildings, existing buildings with stupidly high energy consumption in pumps that circulate water for the air conditioning system. There are horrible things. Energy is wasted everywhere. And but this is actually, even if just making a simple calculation using the simulation code, we would get to this result. Usually in an air conditioning system, the equipment that uses more energy are fans to circulate the air, not the chillers. And so we should be very careful when we use air. We shouldn't use more air than we need. And now let's see ventilation standards. And Noel is an expert on this field. And this is a calculation based on the American standard. How much air do we need to ventilate an office building with 6 square meters with 1 person? So this is not a cellular office, this is an open office in which in each 6 square meter we have 1 person. Okay? And according to the American standard, we should have 4.3 liters per second of ventilation air. Okay? Outdoor air that we deliver to this guy that's working there. With European standard, we have 11.2. Almost 3 times more, 2.5 times more. That's the American standard. I will explain you why. With the current Portuguese law, we would need 8.3. Maybe the best is in the middle. And why is this difference? Both standards, both the American standard and the European standard, are based on the same scientific research and evidence. But they use a different criteria. When the Americans use the same research, but they calculate the ventilation air to satisfy adapted persons. This ventilation air is not determined for health issues. This is way much bigger than we need in order to protect our health. The circulation airflow is calculated in order to bring comfort, satisfaction. And it's called the scientific method to determine these values are based on inquiries to occupancy spaces. and changing the airflow, and people have to change the form, to fill a form and say, I'm very satisfied, I'm not at all satisfied. And also this data is analyzed and we calculate the percentage of people that are satisfied with this kind of ventilation area. This is done worldwide, everywhere. But our nose adapts to others. If we smell, for instance, a perfume, after a while we don't feel it anymore. Okay? We don't feel our perfume. Okay? And because our nose adapts. And this is an adaptive occupant is defined as a person that has entered the room for over 15 minutes. So his nose is adapted. So this inquiry on satisfaction is for occupants that have been on the space for over 15 minutes, not for visitors. The visitor is a person at the exact moment that he gets inside the space. I'm sure that, for instance, in this meeting room, I feel comfortable. I don't feel any kind of bother. I'm comfortable. But someone that gets inside at this moment maybe won't feel so comfortable as I am as you are, because we are here from the beginning and our noses are adapted. Maybe a visitor would start, oh, this room should be a little bit more ventilated. That's the difference. The Americans use the same research to define the ventilation area for adapted persons, and Europeans use study for unadapted persons or visitors. And this is a huge difference. But we could be worse. Because the last law that was in Portugal was replaced in 2013, brought us to 9.7 for the same office building. But it had some issues in the law that actually in practice made everybody use 24.3. This is the fact. With the law we had 2 years ago. And the difference is this one. From the American standard, the European standard, actual Portuguese law, the older Portuguese law, and practice in the last 7 years before 2015. So, this is a huge difference. And this is a fact. I've never done this. I think this is wrong. There were some issues with the last law, and people were afraid, and people always went to the worst case. And the worst case means that we have to multiply this by 2.5, and we will get to 24.3. This is true. I've audited a number of buildings that were designed to build during this time, these 7 years that the law was in place, and each one of them had this figure. So today we have hundreds of buildings in Portugal with enormous amount of ventilation area. There is a huge potential to reduce this energy consumption. So,
both of the energy systems are not running.
Yeah, that's in schools. But in schools they are not running, but in privately or in buildings they are running. It's incredible. And so, what this chart shows is that we should be very careful with the ventilation requirements. They should be done on a very rational basis, and when we are our researchers should give us right figures. Okay? Otherwise, we will never have next week. Never. Also, on the other hand, filters that clean the air actually introduce a huge pressure drop in the air streams, and also represent a significant amount of energy consumption in the fans that I told you before that are the bigger consumers in our efficiency system. Also, all this energy, remember, all the energy used in plants actually degrades to heat and becomes a load of chiller. Because so we have two consumptions. We have a direct consumption in the plant and then indirect consumption in the chiller. All the energy that we supply to the airstream as kinetic energy and pressure is degraded to heat, and this heat will be removed by compressors and chillers that are using lots of energy. So we have so with the last years we have increased a lot in the needs for filters, and we have increased a lot the energy consumption in France due to this requirement. So we also need to have good criteria for indoor air quality. So we have to review ventilation airflow criteria, review filter application criteria, and this last sentence, conciliate requirements for mechanical ventilation with those for natural ventilation, because actually it makes no sense that when we use a mechanical ventilation system, we have to use huge filters that have a high energy consumption, but we can open windows. When you open a window, the open air just comes directly inside the building. Why do you have to clean it with high efficiency filters when you are using a mechanical system? It makes no sense. Lighting and equipment, we have to change the requirements for lighting. Today, most buildings use the criteria of 500 nits, and you are the specialist here. Oh, I'm not saying this is wrong, but the practice is that one. And most buildings have that right criteria all over the floor plan, not only in places where people are working. My desk is here, but I have 500 looks here and here, everywhere. So, people nowadays, most of them use computers. They don't use a computer in 500 looks. And if you have a lower looks level and you have glass lighting, it's a small lighting in your desk. When you read your paper, okay, you turn on the light. I have clients with buildings that have 250 looks everywhere. I say, oh, are you satisfied with this? I don't want to increase it. It happens. Because the other people don't, but they have glass lighting. When they want to read the paper, probably most people turn on the small light they have in the desk. Also, IT, information technology, consumption. Today, computers in the office building represent nearly 30% of the energy consumption of the building. Personal computers. So, it's impossible to have net zero with this load. But we have to take it off the buildings, off the office buildings, and this is being done not by the building industry, but by the IT industry. Because of cloud computing, data centers are being built more and more, and we have cloud computing. Most computers will have just no storage, no processing. We just need an interface with the cloud, and the energy will be used in big data centers that can be extremely energy efficient, and including the heat generated in the IT equipment can be used and should be used for useful purpose. For heating water, for heating fuel, whatever. They should be used for good purpose. So, energy flexibility is a new issue that's been discussed all over the world. And I don't know much about it, but it's the trend now to use energy flexibility, because actually renewables are always changing, and we need to bring this flexibility to the energy use also. And people are thinking, how can we have a more flexible use of energy? in order to adapt easier to renewables. Energy storage is the easiest way, but there are other ways. We can allow for a broader range of acceptable indoor air temperatures with limited time periods. We can create monetary benefits for those buildings that allow the grid to turn off certain loads, certain electrical loads for certain time periods in order to adapt demand and supply of energy. Allow for more flexibility than other. This is being discussed a lot now. How can we make buildings more energy flexible? Now, I get the energy efficiency. I will have to be faster to finish this. We have integrated building design, which is the way to do zero energy buildings as a design process, passive solution optimization, active systems optimization, and efficient technology. Actually, I'm stressing these three, but these three are integrated in integrated building design concept. I will show you what integrated building design is. We have to optimize the building in an effort of the team, the multidisciplinary team, architects, engineers, of different specialities, from the beginning of the conception of the building. And I will go to this next slide. Okay, you can, they will get the slides. This chart here, one image is 1,000 words. Actually, this chart shows the timeline here, and the vertical axis shows the effort. And this line here shows that increasing cost and disruption of the process. And this one decreasing impact on performance. And the traditional way to work is this gray area here. What does this mean? This means that changes in the design that are implemented in the early stages of the design phase have very low cost and can have a very high impact. Changes that are implemented at the end of the process have a very high cost and have a very low impact on energy consumption. For instance, if you want to change the lighting system, after the building is built, it will cost a lot of money. But if you are analyzing different lighting alternatives before, at the beginning, there's no cost. And today, the way we work today is that the bigger effort, bigger workload is done at the construction phase or just before construction. And this effort should move here. We should have more work time, more effort at the earlier stages in order to optimize the design of the building. This chart says it all. And this is not one person work. This is a teamwork. The building is done by architects, engineers, owners. So this is a teamwork, and the effort should be done at the beginning, not before. These charts are from the European project Matthew, which was finished last year, just to study the design process of zero energy buildings. And this shows the design process. There are some parts of design like requirements definition, basis of design, that have a linear process. But conceptual design is an interactive process. We have this solution, then we go back, change the solution, back and forth until we get to the right design. After we have the conception, it's also, again, a linear process. Okay? And then we have renewables when finishing. We can have on-site and off-site or nearby, and on-site we can have building integrated photovoltaics, which is perhaps the best adapted technology to buildings. Heat pumps, solar thermal, shower geothermal. You should be aware of this. There are lots of places in which we have relatively high water temperatures in the underground. Shallow is between 0 and 400 meters deep in the ground. Then we have off-site wind, hydro, solar, biomass, geothermal, other waves, or whatever, all kinds of renewables. These are some pictures of integrated photovoltaics. You know that they can be integrated in the architecture and almost unnoticed. Of course, today the technology is this one. We can see it actually if we look carefully. But hopefully in the next years, this part here will also be photovoltaic. With thin films and new technologies that produce low cost, not so efficient, but very low cost photovoltaics that can be applied all over the world. And we have renewables that are remote from the grid. Of course, we cannot have high efficiency wind power in urban area, and I can tell you better than me. Or, of course, if we have offshore or on top of the hill, when we have very constant and steady high winds, we will have a huge efficiency, huge not efficiency, huge capacity to produce renewable wind energy. But in an urban area, we will never have the same investment, the same delivery of renewables. Or, of course, you couldn't have a hydroelectric in your house or a solar concentrated solar system. And this is the chart of the percentage of electricity in Portugal that's produced by renewables in the last 8 years. And we got 30%, and we got 62%. 2014, we had 62% of renewables in the grid. And this is an issue that's been discussed. If this part of renewables should be considered for the zero energy calculation. My opinion is that it should. Well, of course, there are different opinions, but we should take in account this. Of course, it will be very easy to have zero energy if we get to 100% renewable. All buildings will be zero energy if we use electricity. But we have the means. We have to have very high efficiency. Otherwise, we have in Portugal made a huge investment in renewables, and we have to have this investment. Finally, energy monitoring. To have actually zero energy operating buildings. This chart is from the United States Department of Energy, and it shows 4 different strategies of energy monitoring of buildings. The first one is just to install energy counters, and just install them and do nothing about it. Economy, 0. Energy counters that don't save energy. Second strategy is the first one, strategy 1 plus, allocation of energy costs by department. Okay? We don't, here the electrical engineering building uses this energy, we'll allocate it to this building's energy costs. Typically, and this chart was created based on, I think, around 7,000 federal buildings in the United States. And the result of this strategy is between 2 to 5% energy reduction. Third strategy is strategy 2 plus, analysis and fine-tuning of system operation. And this means adjusting schedules, set points, operating criteria, and so on. And this brings an economy between 5 to 15%. The last one, strategy 3 plus continuous monitoring and commissioning. Fine-tuning and systems commissioning. Systems commissioning means, okay, seeing if the fires are actually operating at the right airflow, the guns, and so on. And the experience shows that we can achieve economies up to 45%. This is huge. So we must have energy monitoring. Also in Europe, we have the ICF project that was completed last year, in which 330 buildings were monitored, and the average, with continuous monitoring, and the average of economy was 90%, but there was a maximum of 33% economy. With measures that at low cost or very low cost that were manufactured components. So what is continuous monitoring is global and partial energy counters. The counters are remotely read by using the web server, and you can access it with a web page anywhere. Online data register reading, graphical treatment of that data and alarming, remote continuous analysis, someone has to look at it, and identification, diagnosis, and quick correction of consumption anomalies. I will just give an example of a client of mine with big swimming pools in south of Portugal in a hotel. Just 6 months later, they checked the bills, the energy bills, and it's a huge increase in energy consumption. They went on and on until they found that the pool that was heated to 30 degrees had a huge loss of water. The pipe was open. They stayed 6 months delivering a huge amount of water flow to the sewage. And only 6 months later they found it. So with a continuous monitoring system, it should be found the next day. Okay. System operation and optimization based on required knowledge from energy knowledge. But actually, before I say goodbye, this continuous monitoring is a fundamental strategy for zero energy buildings, both in Europe and in the United States. And I believe, my opinion, is that it will be mandatory by law in the next years. Thank you.
I think we can have like 10 minutes for this session. Any questions from the audience? Okay, we hope so that there will be a change.
You said that we should, first of all, thank you for a very, very good presentation. And you said that we should use the renewables for the net zero energy buildings calculations.
Renewables in the grid.
Yes. Why?
Actually, if we want all buildings to be zero energy, my opinion is that we have no other way. Because if you have a building that has just 1 or 2 floor plans, you have enough surface area of the building to install photovoltaics.
I can understand that,
But if you have a high rise, you will never have enough area in the building to
yes, but is there
or to balance it. So most zero energy buildings that exist today are 1, 2 floor plans. And unless you change the definition, it will allow renewables to be installed not on site but nearby. Or why totally agree. Because if you can have a much higher efficiency if you use central photovoltaics technology that you wouldn't use in a building. Of course, photovoltaics is the most democratic of renewable energies. It's the same method. Not wind, for instance. Wind, for instance, you can use a wind turbine in a building, but you will never have the delivery that you will use offshore or over the mountain. Well, I think we are discussing this. That's my opinion.
Okay, no, I can understand the rationale behind that. But my point is, if we forget the first part of the definition of net zero building, the energy efficient building, and if member states can define what a large amount of energy and nearby, and even the definition of near zero building, with 60% of the electricity being produced by renewables, almost our buildings can be almost net zero buildings without being efficient buildings.
Well, I'm sure it will not happen this way. I'm sure it will not happen
But
this way.
is there a risk, right?
Yes, that's a risk. But I think there is good will, even if we have partial answer in the legislature. There is good will. People are concerned with the environment. But that's not just net zero. We should be efficient also. And,
We should not forget that part of the definition of net zero. We should not forget the third part. Exactly.
It's actually, there is another issue. I think we are learning. This is new ground. We are going to new ground. We are learning step by step. Because actually, if just in theory, if all buildings were zero energy, the grid wouldn't have to supply anyone. Everybody was autonomous energy-wise.
If you have enough storage,
There would be no grid. Okay, that's theoretical. And would people be so willing to spend money on efficient technology? I don't know. I think we have to think about it. I think it's good to have a cost for energy. And if we have, even if we achieve 100% renewables on the electrical grid, of course, electricity will always have a cost to the user. And if it doesn't have a cost, people won't use it efficiently. Well, this is new ground. We have to discuss all issues. And this issue in Portugal, I know it's been discussed, if it should be considered or not. But actually, there is a European study that will bring some rules on the definition. But it's not published yet. And it's difficult to reach an agreement between 28 countries, speaking different languages and different cultures. It's a big,
Very different energy difference.
hopefully we will reach a good solution.
Even the conversion factors are changing very much from something to something.
No, I was just.
You were about to.
Moving towards the network requirements does not eliminate the other requirements. I don't think there will be that big of a risk of not having energy efficient buildings. When you're moving towards the requirements, the other energy requirements will still be there, even if it's if there's a net zero energy balance.
Yes, I think so.
Quality requirements.
You will never have zero energy without energy efficiency. But, as I said, theoretically, if we have already 62% of the electrical energy produced by renewables, we are very close to 100%. And if a building uses just electricity, it could be defined as building. If the definition is that open, it's a risk.
We can use fuel cell in building. Fuel cell.
Fusion and
Fuel cell.
sorry, fuel cell.
Like
But fuel cells using
chemical, not
yes. What would be hydrogen? The gas.
hydrogen.
Natural hydrogen. Hydrogen. Okay. If you use hydrogen, for instance, depends on how you produce the hydrogen. If you
From
produce,
what we are going to drink water to.
but you use energy. If you produce hydrogen using renewables, this is not defined. I don't think anyway. My opinion as a technician is that if the hydrogen is produced by renewables, for instance, if you have a wind mill on top of the mountain, and instead of installing a big wire to the top of the mountain, you have a small hydrogen production unit, and to transform electricity into hydrogen, this hydrogen will be removed. Could be classified, of course, as you know.
And like a fuel cell, like renewable, you can use fuel cell from net zero building, fuel cell.
I would say that only if the hydrogen would be produced by renewable energy, because to produce hydrogen, you use energy.
But at the end, if you want to use electricity, this process has lots of losses, and it doesn't work. It's better if you need electricity, you produce electricity and use it, even though you have to
Less losses.
transform it. But just to add something, I'm electrical engineering, more dealing with electric vehicles, but I'm also interested in this. I think even if the buildings are more than zero, if they are negative energy buildings,
Yes.
well, it depends. I mean, if they generate electricity in excess, you can always try to sell that energy or charge electric vehicles and try to solve other problems: pollution, energy dependency from the foreign, and so on. So that there's a long way to go, and I think it's a question or a comment is how do we? I totally agree with your presentation, but the question is also how do we get this into people? We were here talking about air quality, and we were almost dying without oxygen because the door was closed.
It was for the problem of noise.
I know, there's a problem of noise, there are natural light here, no natural air. I know, that's a question of education, and I totally agree with you that people should be aware of this and take this into consideration in designing process, because now it will be much more expensive to open windows or light bulbs to have natural lights or so on.
That is limited. Yes, that's has to be done to get to net zero. You have to maximize natural resources in the building, natural lighting, natural ventilation, optimize the passive solutions. You can have, if you design correctly a building from scratch, from the early design phase, using building management technology tools, you can reach a building that needs heating or cooling very small number of hours per year. It should be.
I think some work has to be done also on the education of people that are already in the field working, because most people here are still studying, maybe PhD level or so. But for engineers that are designing buildings, maybe some education programs, set up education programs with engineers orders and also with employee payment. Contractors, yeah, okay. Because at the end, they define many things at building level. Okay, so
Yes?
From your point of view, the requirement that the EPD has on life cycle cost evaluation of projects, wide do you think that this life cycle cost analysis should be done in order for the net zero energy to become net zero global? Because energy is just a narrow perspective on global.
If we should do the life cycle cost
Because
or not.
the EPD also refers to
Yes.
this, that it establishes some kind of artificial price for CO2, equivalent emission, mass emission, and it even defines the evolution of the prospective evolution of the CO2 price or how do you see this? Is that zero
Actually,
the whole thing that we should be concerned on?
Actually, this is a very important issue. Countries are discussing it. How to, because we have to do all this with cost rational. The life cycle cost should show that the investment there is a return on investment. We should do, this is another challenge. Recently, most countries are discussing this now. Last year we had here in Portugal a guy from TVVL and especially show how they are doing it and how they are trying to do it. And actually it will bring other variables to the cost analysis. Because, for instance, productivity, other costs that if energy costs in a building are very low compared with wages of the occupants of the building. So if we deliver something, if we have a building that increases satisfaction of the occupants, and with that increases productivity, and we can somehow attribute a value to this increase in productivity and use this value in the analysis. This was the way the Dutch guy showed us that they were studying this just in this simplistic way. He spent half an hour explaining it. Basically, it's a very important issue and difficult to solve, and the countries are thinking of how to, because we have to do all this and also be cost effective. For instance, the example that I showed, we have solar thermal, heat pump, and photovoltaics. I just explained it technically why. I didn't show you figures. This costs this, then the heat pump costs this, and the photovoltaics costs this, and so we will have return on investment. I didn't show these figures.
It was a very interesting presentation and discussion. Thank you, Carol. Thank you, everybody. We have 15 minutes of this. No, now we start directly.